Today's video is about Beer-Lambert law of spectrophotometry, and to solve few problems those found in different competitive examination, for example NET. So what is Beer-Lambert law? On passing of a beam of monochromatic light through a medium, that is absorbing absorbing solution, the rate of decrease in intensity of light with the thickness of the solution is proportional to the intensity of incident light and to the concentration of the solution. So considering a thin layer of medium, so this is a thin layer of medium and its concentration is C and the light intensity is I, then rate of decrease of intensity of light, that is di, with the thickness of solution, that is dl, that is proportional to concentration of the medium and also the intensity of the light. So this is our formula from this law, that minus di dl is proportional to C into I, and accordingly we find that di dl is equal to minus k double dash Ci, where k double dash is a constant. So we can rearrange this equation like this, and then integrating both, integrating this equation with a boundary condition, that is when L is equal to 0, I is equal to I0, and when L is equals to L, I is equal to IT. So from this we get ln IT by I0 is equal to minus k dash Cl. Then if we finally find this equation, but this come from here like that from here you can say IT by I0 is equal to e to the power minus k double dash C L, and then this equation, then we find this equation. So you have to identify this equation. This is very fundamental equation. So I write at the top of this slide. Thus, the Lambert-Beer law states that the intensity of transmitted light, that is IT, which we find that is intensity of transmitted light, is an exponential function of rising number of light absorbing particle in its path, and so the product of the molar concentration and depth of solution, depth of the solution. So we rewrite this solution like this. So how this appears here? From this equation, actually we can rewrite this in the previous form, that is IT by I0 is equal to e to the power minus k double dash CL. So if I take ln it by I0, then it will back to what will come is minus k double dash CL, and this is, if I convert this ln to log, this will be, we have to multiply 2.303 log it by I0. Actually this ln is, if I convert ln to log, we have to multiply with 2.303. Rest is same. Then if I take log of this it by I0, then it will be one by 2.303 into minus k double dash CL. So this 1 by 2.230, this is actually 0.4343 k to the power k double dash CL. Keep minus here. So then if take it by I0, this will 10 to the power, this will be 10 to the power minus minus this minus 0.4343 k double dash CL, and then it got this equation, finally, and then we take this portion k double dash into 0.4343 is equal to epsilon. So this epsilon is called molar extinction coefficient, and this value is, I already said, and the value of this epsilon is specific for a given substance and for a given wavelength of light. So next is I rewrite the first equation, which is most important equation of Lambert-Beer law, like this. And now this portion, this it by I0, this is the proportion of light transmitted and is called transmittance, and it is denoted as T, and it gives the ability to transmit light as an exponential function of the concentration of the solution, and the logarithm of its reciprocal is called optical density or absorbance. So if I keep this equation here, so I have to take this the reciprocal of logarithm of reciprocal, that is 1 by t. I have to find the log 1 by t. This is called actually absorbance or optical density. So to get this, as here E is there, here E is there, so we have to take ln first. Then we convert into log, so then log t will be the epsilon Cl, and then absorbance is, that is log 1 by t is equal to log I0 by IT is equal to epsilon Cl. So when we plotted this log I0 by IT against the concentration of the solution taken in a definite column of definite thickness, then if I plot this, log I0 by IT against C, we find a straight line, and the slope of this straight line will be epsilon L. In the second part of this video, we're going to solve few problems. One is, if 0.05 molar proline hindrance complex has an absorbance of 0.15 at 520 nanometer in 1 centimeter cubed, calculate the molar extinction coefficient. So we know the solution, this formula, that absorbance is equal to molar extinction coefficient into concentration of the medium and the thickness of the medium. The thickness of the medium is 1 centimeter. Absorbance A is equal to 0.15, and this is C. So we have to identify the molar extinction coefficient. So epsilon is equal to then absorbance into concentration into L. That is, the absorbance is 0.15, this is 0.05, and this is 1. So the answer will be 3 per molar per centimeter. So this will be our answer. So in our second problem, molar extinction coefficient of H2O2 at 240 nanometer is 0.04 per mole per centimeter. Calculate the concentration of H2O2 in a solution which has absorbance of 0.6 in 3 centimeter cubed. So we know that formula absorbance is equal to epsilon into concentration into thickness of the cubed. So we have to here identify the concentration C is equal to then absorbance and then molar extinction coefficient and L. And here absorbance is given 0.6, molar extinction coefficient is 0.4, and L is 3. So our answer is 5 mole. So in Another problem, molar extension coefficient of molanodialdehyde is 0.155 millimole per centimeter, and we have to identify the concentration of the solution having an absorbance of 0.31. So our formula is absorbance is equal to molar extension coefficient into concentration into L. So we have to identify the the concentration, that is, so here absorbance I put 0.31, molar extension coefficient I put 0.55, and L, conventionally length of cuvette is 1 centimeter, so I keep it 1. So the answer is 2 millimole. So thank you for watching this video and your patience.